So I'd like to tell you today about how we might understand geometry as a particularly well-behaved compression algorithm and its relation to a talk that Bartek gave last week on kinematic space. So this is work, some of which has been published. It's with Bartek and myself, as well as two excellent graduate students. Those are Lampros Lampreux and Sam McCandlish. Sam is here. There's a second paper which really should have been published a long time ago, but hasn't, and that's also with Patrick Hayden. So I said Bartek last week gave a beautiful talk on the geometry of kinematic space. So if you haven't listened to it, if you weren't there, you should go watch it online. And given that Bartek did such an excellent job, I'd like to exercise my right today in sort of a less formal setting than at that conference to sort of talk a little more broadly and put these results in some perspective. And really what that means is I'm going to sort of speculate a little freely. So I think to put this in the context of discussions that have been happening here, our point of embarkation will really be the discussion that we were having just a few days ago about state-dependent linear operators or non-standard interpretations of quantum mechanics for understanding observables behind black hole horizons. There seems to be an emerging consensus, and I'll emphasize possibly, that we're forced to make a rather unpleasant choice between the breakdown of effective field theory at the horizon for typical states or some sort of nonlinear measurement theory. And in this nonlinear measurement theory, if we're really trying to save effective field theory, it's by some sort of entropic theory of gravity. The interior geometry is built out of whatever it is that the exterior happens to be entangled with. So this is kind of the heart of ideas that in the work of Papadodimas Raju or ER equals EPR and all the other names might attach to those diagrams. I think we should really take that latter option very seriously, that we should sort of ask ourselves how well we can understand geometry using tools of entropy. It's a program, I guess we're ahead just a little bit. So, I mean, it's a program that's been very successful. A lot of people in this room have, made a lot of ground out of thinking seriously about gravity as an entropic theory. I know Eric is here and Ted is here. So many people have found this to be very useful. So I think there's good reason to believe that we should continue in this direction, even if that last slide made it sound a little preposterous. And so yesterday or Tuesday, Joe issued a challenge. I'm going to paraphrase. This might not be the tone that he expressed it in, but he really said, you entropy people need to answer for the nonlinearity in S equals A.
You need to fix this.
Pardon?
You need to fix this.
Okay, well, I heard it as sort of this curmudgeonly claim, so that's how it's written. My response is let's not, actually.
Doesn't quantum error correction fix this?
Yeah.
I mean,
in some context.
So we're going to have to confront this idea at some point, but I'd like to say that our day of reckoning will come later. So instead, what I'd like to do is see how usefully we can understand geometry using entropy. And we're going to find our way to Joe's challenge one day. We'll make our way there, but let's not attack this head on. Let's face these challenges as they arise. And so while we all want to ultimately solve the black hole information problem to understand what happens behind the horizon, I think, at least for me, it's hard and I'm just very confused. And so I'd like to make a metaphor because I can't resist and just say, black holes are the Olympics. So, every few years we formulate some new ideas about quantum gravity, and then we all come together to see who's champion. And, the testing ground, the competition is what does it predict for black holes? But usually it's a good idea to train first. So maybe some of us here are been training their whole lives. Maybe some are just natural athletes. I'm not going to count myself among them. So before I attempt to tell you how entropy tells us what happens behind the black hole, I'd like to do some warm-up exercises. And so on day one of our training program, let's try to understand entropic and information theoretic quantities as geometric probes in a less competitive environment. So I'd like to do that, and I'd like to give us some training goals for quantum gravity. The first training goal we'd have to answer is, what states have good geometric duals? So we want to know to what extent is geometry determined by entropic CFT quantities, and what information about the state is necessary. We'd like to ask, is there some sort of entropic interpretation of the holographic RG and the emergence of this radial direction? And what is the entropic meaning of areas in space-time? What is that area really counting? What are those states? So I think there's been some hints for these training goals from MERA. So we've learned that for a CFT, one can efficiently represent certain low-energy states, in particular the ground state, by some network of unitary operators. And Brian Smigel suggested that the structure of this lattice really is the structure of the vacuum state geometry in a CFT, that it sort of has the coarse-grained structure of the hyperbolic disk. So that's sort of part of an answer to question 1. The MERA also gives part of an answer to our question 2, in that lattice points deeper into the bulk encode IR entanglement, so it's organizing entanglement with scale, so there is some suggestion of the RG in this tensor network. But it's also interesting is that when we cut out some region in the center of the MERA lattice, we remove some number of unitary operators that's sort of proportional to the area of the cut. And so we're able to prepare new states and feed them back into the network. And the number of new states that we can prepare is really given just by the number of cuts along that network. It's measuring the size of that infrared Hilbert space. And so we see exactly as well that the MERA gives us some interpretation to what this entropy is counting when we talk about the entropic interpretation of an area. So really that the MERA lattice seems to answer all of these questions, at least in the context of the ground state. And so I think this is very intriguing and very suggestive that this is a worthwhile avenue to ask these questions.
If I imagine like the exact ground state, these tensors are fixed to some numbers, right? So
that's right.
So when you cut it out, you just get one state. You don't get...
No, I mean, this is not a state. Oh. What really you should understand the exterior of this network is being an operator. And it's an operator that I think in some instances it's called like a descending superoperator. It takes this infrared state that you input into the network and prepares a UV state. So by changing the state that I choose as an input, I get a whole number of different states out as output. And the number of different input states is just given by the area of this cut as measured in the lines crossing it.
So I'm actually just curious. Is there a reason why you want to specifically talk about MERA instead of just tensor networks more generally? I mean,
No. MERA is just my nice example about the ground state. It's something where things I understand quite well, and certainly we've learned a lot from you guys since the MERA story was first articulated. But this is just sort of where I'd like to begin. The question I want to ask is, this is all beautiful in the ground state. What is the more general story? And so we're going to convert our training goals into concrete exercises. The things we have to do is figure out what is the analog of the MERA network for non-vacuum states. What are the rules for building the right type of network? You could build an arbitrarily complex network for some state. It's not necessarily going to tell you anything about the geometry. We want to know what boundary data determines this network. And we want to be able to tell you, if I give you some tensor network for a state, when is this network geometric? When does a state have a good geometric dual? We like to ask, how do we interpret the holographic RG in terms of, the radial direction in these tensor networks? And what is the entropic meaning of subregions of a tensor network? So what is this entropy counting in terms of the different states that they prepare? I'd also add a fourth exercise that wasn't there initially, and what is the right language to translate between this discrete language of tensor networks and some continuum language? So how do we convert these sort of nice toy models into something more reminiscent of a continuum conformal field theory? Oh, good. Anyways, so let me review now kinematic space. So Bartek went over this last week, so I want to be rather brief. So we'd like to describe geometry in terms of information theoretic quantities, but these are not local observables in the geometry. They always correspond to some sort of integrated quantity. And so it's natural then, I think, to describe geometry indirectly by some sort of integral transform. In the context that I'm going to be talking about today, in two-dimensional bulk spatial geometries, we want a dual space whose points correspond to geodesics. And we're going to call this the associated kinematic space for our geometry. The way I want to think about kinematic space is some sort of translator. We have the sort of information theoretic language describing the state, and this information theoretic language can most naturally be described in terms of this kinematic space. And then there's some sort of integral transform that then tells us about geometry. And so this is sort of a natural translator between these two pictures. It's sort of an intermediate simple step. This transformation from real space to the space of geodesics is exactly the concern of a field of mathematics called integral geometry. There's two classic results from integral geometry, the first of which is the radon transform. This is something that's already shown up in holography. The radon transform of a function on the real plane is just another function on the space of straight lines that we get just by integrating over a line. So take the function on the plane, integrate along some line, and it defines a function on the line. If one result has shown up and been important for holography, it's a good guess that the other classic result should also be useful. That other classic result is the Crofton formula. And the Crofton formula says there's a very nice way to write the length of a curve. If you want to write the length of a plane curve, I'm going to integrate over this space, this kinematic space we'll call it, the space of lines in the plane. And the weight on that integral is just going to be the intersection number. So for every line, I count how many times it intersects my curve. And that's the weight. And I do the integral, and it gives me exactly the length of that curve.
How old is this formula, just out of curiosity?
Yeah, I don't. Do you remember?
Space, I think 1870.
Yeah, it's a classic result.
Okay.
Yeah.
But this only holds for totally symmetric spaces.
Yeah. So for a long time, and still, if you read a lot of the papers on it, they really say that integral geometry is really the study of symmetric spaces. And so actually, in the mathematics literature, we found nobody had written down a Crofton formula for spaces where it was not determined by symmetry. So you might wonder, are we a little crazy to try to do it? Is there some appropriate measure that gives me a Crofton formula in a more general geometry? And the answer actually, although we've never found it in the mathematics literature, is yes. So there is a natural Crofton form that reproduces the length of any curve in any geometry whose tangent space is covered by boundary-anchored geodesics. The Crofton form is given here just by the second derivative, the function I'm calling s of uv. S is just the length of that curve, but I'm going to, for purposes in the future, measure that in terms of units in 4G and call it the entropy.
Can you just unpack that?
Yeah, so I realize there's meant to be a diagram here. So just let me label my coordinates because I realized that disappeared.
Can you turn the light on?
These coordinates, u and v, are just the left and right endpoints of my interval. At times, it will also be useful to talk about its center point alpha and its half angle alpha. So I'm going to always imagine that this is just on a circle, which I've drawn large here. You wanted me to unpack this statement here?
Yeah,
Yeah, so this is just a restriction that's probably not necessary. What I really want to do is talk about a Crofton form for a space where the only data I need are these boundary-anchored geodesics. So the only things that I need are essentially the geodesics that encode entanglement entropy. That's not generic. So there's going to be, if I looked at sort of a generic tangent vector in some space-time, that it's not necessarily a tangent vector who's minimal for its boundary conditions. And so if I want to sort of do this, do this sort of philosophy of the Crofton formula, I'm going to need sort of more data. I'm going to need non-minimal geodesics. So I think it's very possible that you have a Crofton formula that works in those cases. I just need sort of extra ingredients.
So I guess the thing I was hung up on was if you just take some point in the tangent space at some point, I can certainly solve the geodesic equation this way and that way, going away from the point, and either it's going to get to the boundary or it's going to hit a singularity.
That's right.
So it seems unless there are singularities, this isn't a very.
No, but it could reach the boundary, but it might not be the minimal geodesic for those boundary conditions. So it may not be.
That's important.
That's important because what I really want to do is here we could just call this a length and it wouldn't matter, and we could build a Crofton formula that uses all of that data. But what I really want to do is talk about entropies. So I think it's a very interesting question how I tell this story where I have more information theoretic quantities that I can use to describe all of those geodesics, even if they're not sort of globally minimal. The story that I only understand at the moment requires me to use entanglement entropy only.
Are you assuming asymptotically ABS boundary?
I am, yes. So it will be natural to interpret this density as the volume form of our kinematic space. If I do that, a nice example is just the kinematic space for the hyperbolic disk, and then kinematic space is Lorentzian de Sitter space. You might ask, why is this a Lorentzian space? There's actually a very natural interpretation of that causal structure, as Bartek told us last week. So if 2 points are time-like separated, what it means is just that the interval for one is contained in the interval for other. So actually being causally accessible is actually very operationally important. It means, well, actually I'm kind of reading the causal direction the opposite way here, but being causally accessible means that if you give me the larger density matrix, I can trace down and get the smaller one. That's a kind of a nice interpretation of causally accessible. If things are light-like, of course, it just means that they share a common endpoint. And if they're space-like, it means, of course, that their intervals they do not overlap. And so now sort of causally inaccessible, really operationally meaningful in that I cannot get you the density matrix just by tracing out degrees of freedom simply from one to get to the other. So this causal structure, I think, is very intuitive. What does this Crofton formula look like when I try to compute the length? Well, let's just take two simple examples because I would like to use them at the end of my talk. So let's just take this convex surface. It's just a circle. And now we look at all the geodesics, starting with the ones that are tangent, and then keep going through as they get larger. So at some half angle here, alpha, they're going to start touching. And we'll keep integrating all of the ones until they kind of reach the other side and no longer intersect. And so I just really integrate over this strip in kinematic space with intersection number 2. Each geodesic enters once and leaves once. If I look at some non-convex surface, the integral actually is a little more complicated. This light shaded region, I'm integrating with intersection number 2, but there's all these other regions where I integrate with intersection number 4. This is rather sort of easy to understand. If I think about some non-convex surface, what it means is that something can enter and leave and enter and leave. So, if it was convex, things that could only enter and leave once. And so these regions where I integrate with intersection number 4 are just these geodesics with higher intersection number. So this will just be a useful picture for some statement that I'd like to make at the end of my talk. There's also a nice interpretation that we can make of kinematic geometry. So that volume form we chose was chosen to be geometrically useful. It reproduced lengths. But it also has a very simple information theoretic interpretation. I think this is kind of a nice, pleasant surprise. So let's take some region in my kinematic space. I'm going to just call the regions A, B, and C, and draw the boundary of their causal diamond. And then I can look at this little plaquette up here. And I can ask what happens when I integrate my volume form over this region. And what I get is just the conditional mutual information. So what we find actually is that the local geometric data in this network is telling me about information theoretic quantities. These were things that were integrated, that we had to use geodesics in the real space to measure, but now there is just some local form which tells me their quantity. So I'd like to make a jump just to talk again about MERA, having sort of reviewed kinematic space. Are there any questions about that before I do? Nope. Okay, good. So let's talk a little bit about MERA and holography, just to remind us of some things that we probably all know well. The MERA network has an additional spatial dimension than the boundary state, and it's related to the length scale of entanglement coarse graining. And so it's very natural to view MERA as related to holographic geometry, but this is a statement that has been made rather precise. What we can do is associate a fixed distance to crossing each line of the network. And then the corresponding metric one gets is really just sort of like a discrete spatial slice of ADS2. But it also is very beautiful in that it realizes the Ryu-Takanaga procedure for calculating entanglement entropy. So if we look at some boundary region of length L, and then we consider some minimal cut in the MERA network that is homologous to that same boundary region, if we look at the length of that cut, as we just said, using the line crossing metric, it scales like the logarithm of the length on the boundary. And so the density matrix for the boundary region is here, at the edge of the UV edge of the network, is prepared by IR density matrix that then filters through this region. And so the entanglement entropy of the density matrix here is bounded by the entanglement entropy of the IR density matrix. And the Hilbert space in the infrared, as we said, is just given by log L. So we know there's an upper bound to the entanglement entropy that, again, just sort of scales like some constant time log L. And this scaling is really realized for the ground state. That's why we think that this is a reasonable approximation to the spatial lattice, why there's a good correspondence between tensor networks and geometry, is that this line crossing metric is a good measure of entropy.
When you say realized, do you mean with like of order?
That's right.
How do you know that? Do you mean by numerical calculations?
No, my statement is only that in the ground state that we know this scaling is correct. So we know the entropy should scale like the logarithm of the length.
In CFT, you know that.
That's right.
But here you're just...
No. That's exactly what I'm saying, is that this is an upper bound, and if this prepares the CFT state, it realizes that upper bound.
Okay.
Well, we know it does.
But how do you know it's the same constant?
Oh, so I am being very vague about constants here.
Up to the choice.
I mean, I think it's plausible that it's a border that just because sort of by generosity.
By generosity, but it certainly has to be true if this is the CFT ground state. And that's the only point I wanted to make, is that there's a good correspondence between geometry and the network because this is realized. If it wasn't, this would not be useful. You wouldn't say you got the Ru-Takanagi procedure using the line cutting metric.
So here you're really thinking of this as actually preparing the ground state of like n equals 4 super Yang Mills theory.
Yeah, I mean, we haven't done that for n equals 4 super Yang Mills, but we can do it, say, for the Ising model.
Yeah.
And that works beautifully. But I think there are some incongruities with the standard picture, and I think they're worth thinking about. The first one, that in assigning a metric to the MERA network, we really just assumed the Euclidean signature. But that was not derived. It was not necessary. And I think this network actually really does have a natural causal structure associated to it. And this really might suggest to us there's a better metric to put on, and one that has a Lorentzian signature. So if we look at some region on the boundary, there's a concept called its causal cone. And the causal cone is just the region of the network where changing the tensors changes the state or the density matrix in this region. There's also something that I might call an exclusive causal cone. And that's just the region of the network where changing these tensors only affects the density matrix on this region. So there's inward-going causal rays and outward-going causal rays, and these naturally form a causal structure at every point in this network. And so this looks very Lorentzian to me.
What was wrong with the phrase domain of dependence?
Pardon?
What was wrong with the phrase domain of dependence?
Well, again, here is the domain of dependence of this region. Yeah. I'm just saying that I can do this at any point. So I did it at the boundary, but I can take any network line, and then I can go up by looking at all the tensors that affect those sites and all the ones that only affect those sites. And this is something that I can do locally in the network.
He's just complaining you called it exclusive causal cone instead of domain of dependence.
Yeah, I mean,
I'm petty that way.
this is the concept about tensor networks, and when, we're going to rename everything about tensor networks into some statement about Lorentzian geometry, but we haven't done that yet. And I'm still trying to convince you that these facts about tensor networks are good facts about a Lorentzian geometry. There's also another incongruity that I'd like to bring up. Oh, wow. A particular node in the network corresponds to some unitary transformation that affects a region of a certain size, but that can't be localized on any smaller interval. So if I look at my MERA network, and I pick this node here, which is in blue, if you can see it, adjusting this tensor affects the state in the orange region, but it's something that cannot be localized on the boundary in either of these gray regions. So it's natural to associate it, I think, to some region of the boundary or some geodesic, as opposed to, say, some sort of ADS scale size region at the top. In particular, this point is distinguished on this geodesic only by my choice of cutoff. I can change the cutoff here by making my network longer by adding more nodes on, but this tensor is still just the tensor that affects that region. And so you might want to associate it with the entire geodesic with some boundary interval as opposed to some local region in the geometry. So those are two incongruities. There's more that one can discuss, but I am already short on time. So I think the picture for MERA is not perfect. But I think that we can translate the workings of MERA into general principles for constructing tensor networks. And so the question that I want to ask is, what is MERA really doing that's useful? Why is MERA telling us anything about geometry? And I think if we think about it, MERA only realized the Ru-Takanagi procedure because the links cut are assumed to be uncorrelated. And if they're uncorrelated, distances and cuts are both additive and locally measurable. If I'm calculating the length of some RT surface, I do a cut here, that's some distance. It's also some entropy contribution. And it doesn't matter the other links that I cut along that Ru-Takanagi surface. If I cut some link here and then I cut its reference link over here, I would have thought that had some length and this length, but they cancel out in the entropy. So I think tensor networks realize geometry because cuts are additive and locally measurable. And this is really the heart of the connection. I think this is equivalent to saying that the Ru-Takanagi surface in the tensor network encodes a compressed state of the interval. What that means is that I have removed all the mutual information between the edges of the network along that Ru-Takanagi cut. And so this, I mean, you might say this is not exactly true about MERA, but if we're going to build a tensor network, perhaps one that works even better than MERA, this is what should happen. And so I'd like to elevate this to a principle. And so it's going to be my first principle of building tensor networks for gravitational states. And that's the tensor network should encode compressed states along the Ryu-Takanagi surfaces, which I'm going to put in quotation marks for the moment.
So what is the definition of compressed state?
So I was being a little bit vague. What I really mean is that if I take this cut, this Ryu-Takanagi cut, that if you take any link, it has zero mutual information with all of the other links across that cut. So what you can see is that the purpose of the network in some region below the Ryu-Takanagi surface is just to remove all of the mutual information between these degrees of freedom as I go up. So they're compressing the state. They're removing the unnecessary correlations. And what's left then is just the correlations along each cut that they carry with the rest of the system.
So somehow this is true at large C or something? You should
Yes.
have to prove this for some...
Yes. So, well, to prove that one can perform this compression algorithm is actually a complicated job, and so it's not entirely worked out. It's something we're hoping to finish soon, but we'll see how long that actually takes. So at this particular moment, what I'm making is a conjecture about a procedure we should be doing.
So it would be sufficient, I guess, if the network in between the Ryu-Takanagi surface and the boundary was an isometry from the Ryu-Takanagi surface to the boundary?
Yes, indeed.
Yeah, that was the thing that we had to do this in some cases.
That's right. So, I mean, I think these types of networks are very similar operationally to the types of networks you've been working with. I think they're slightly different, but I think there's going to be more similarities than there are differences, and I think you'll see as we go on.
There should be a better definition than that, though, because that's kind of too strong, I think, what happened in our thing. It's kind of...
It is. So, I mean, we're not requiring, what I'm saying here does not require maximal entanglement across these links, for example. So in your picture, all of these are maximally entangled. I'm making a slightly weaker thing. So what you could imagine is that each of these links carried like an entanglement weight. So they're not maximally entangled. The key part is just that they're uncorrelated. And so I could maybe put a number on each of these. It could become a weighted network as opposed to a network, and you just add up all of those numbers. The key, and all that it's saying is that this link represents a little different piece of the network. I have not cut the network up into equal lengths, but they're different lengths weighted by that cut. So let's just look at this network for a moment. And I, again, have highlighted 3 regions that are contiguous, A, B, and C. And now let's look at their entanglement entropies. So first, I'm going to take the entropy of AB and draw its cut, and the entropy of BC and draw its cut. And now I'm going to subtract the entropy of ABC, and draw its cut there, and I'm going to subtract the entropy of B. And so if all these cuts are really uncorrelated with each other, that these just cancel along all of these cuts. So most of the cuts in this picture, these cancel, these all cancel, and we're just left with cuts here. And so we have some cuts that come with positive signs and some that come with negative signs. And if you look at this alternating sum, you probably recognize this. It's just the conditional mutual information again. And the conditional mutual information, we said, is now determined by this localized piece of the network. So I'm going to make this kind of a second pseudo-principle. So I'm going to say that conditional mutual information is encoded locally. I'm going to put a little star here because actually, if you think about it, it actually follows from the first statement. But I want to kind of highlight it as a second principle because it's going to make some of the connections more clear. So let's begin in some basket weaving 101. I want you to notice that the area element here in kinematic space that encoded the conditional mutual information looks very similar to this small sort of plaquette of the tensor network, which also encodes the conditional mutual information. I think this picture should look fairly suggestive to you, and I hope it is just a small leap to say that I should probably think about MERA not as describing the hyperbolic geometry, the real space geometry, but its dual space, this de Sitter, this kinematic space. So what we are calling the Ryu-Takanagi surfaces really are these domains of dependence in de Sitter. And the tensor network nodes, as I suggested before, are not describing some small ADS region of the hyperbolic disk, but are describing geodesics, some region about that geodesic in the dual geometry. So making this change neatly resolves all of our lingering unhappiness with the standard interpretation of MERA as the hyperbolic disk. So I solved all the problems that I told you about.
Sorry. So if you now give up the picture of this network as living in ADS,
Yep.
then why does the length of it still encode the entanglement entropy?
So I'm going to explain that to you. I mean, so as I told you is that in this dual space, what I really want to think about, is that these cuts are all uncorrelated. And so the statement is that entanglement entropy in this dual space is encoded along the boundary domain of dependence. So you can think what the causal evolution in this space doing is just removing correlations. And by the time that you've reached the boundary domain of dependence, you've removed all of the local correlations, and you're just left just with the correlations with the rest of the system. And so cutting the network along this domain of dependence now gives you the entropy.
So, excuse me. So,
Yeah.
so what are the lingering unhappiness? I mean,
Well, I gave you my two problems with the interpretation of MERA as the hyperbolic disk. And now I reinterpreted it, and those problems have gone away.
so what were the problems?
So the problem I listed was that the MERA network has a natural causal structure.
So this and this.
Yes. Well, but yeah, about yeah, exactly. And also I suggested that nodes in the network really should be identified by their effect on some interval, as opposed to being localized spatially. So there was no sort of distinguished end of the geodesic that we should sort of localize that around, that they should be associated sort of equally with any point on the geodesic in the bulk.
So how does this resolve this causal structure, puzzle, or whatever?
So I'm saying that this network is this space. This space has a causal structure. The causal structure of MERA is the causal structure of de Sitter. And that these points are associated to geodesics. Because a point in this dual space is a geodesic in the hyperbolic space. So I would say we didn't just find kinematic space for the ADS vacuum. So while it might have been confusing what the right generalization of MERA was to some arbitrary state, I do have a generalization of kinematic space to many other geometries. So maybe if we think about it, we have some principles here that allow us to build more general tensor networks. So let's say, using our principled approach to understanding what MERA is doing and our knowledge of kinematic geometry, can we find efficient tensor networks for more general states? So what we need to do is sort of slightly modify our principles. We're just going to rename them. So we said before that we're going to compress states along the Ru-Takanagi surface. We're just going to change the name. We're going to say we're going to compress states along the boundary of the domain of dependence. And the conditional mutual information is now encoded locally by the volume of kinematic space. So let's see how far we can go.
How much more time do you need?
How long have I been? 30 minutes now?
35, I think, roughly.
But we started late, though.
2 minutes.
Okay. And then I have
So, just how much?
10 minutes of questions, so I'm going to speed through.
Well, so what are you saying? How much time do you think you need?
I will probably end up using most of my question time.
We've been asking questions.
Yeah, they've been.
Okay.
It'll be worth it.
Okay. We do need to allow time for the second talk.
Yeah, but my talk may occupy my 10 minutes of questions, and I will live with those consequences. If that's okay with the organizers.
That sounded like a declaration.
Let's continue. We don't want to waste any more time. So this requirement that the network performs compression is actually an extremely powerful constraint. So what it means is that correlations between subsystems, say subsystems A and C, cannot be created in an arbitrary place in our network. So if I created a correlation in the network up here, it means that I would have to have correlations that filter through this domain of dependence, and that's not allowed. That's banned by our principle. In a similar way, they cannot be created down here. Otherwise, there's correlations along part of the network. And so there's really only some small diamond in the network where correlations are created. And so information really flows in our network along light rays, and it all originates locally in particular places of the network that I can identify. So if we consider the conditional mutual information again, if all these boundaries are uncorrelated, each line in the network gives an additive contribution, as we said. And the conditional mutual information is just the difference in lines cutting the top and bottom of this colored region. But the difference in the number of lines crossing the bottom and top is just the number of lines that are inserted into the network. And so this density, we see, is really just measuring the number of isometries, the number of correlated pairs that I am inserting into the network. So this is a very nice interpretation that tells us sort of how to build our network using this volume form.
Jamie, Is there some geometric quantity in kinematic space that computes that?
That's right. So as we were saying before, this is just the volume of kinematic space.
So there's a volume in de Sitter space?
Yep. Well, yeah, we can call this a volume. I mean, really, what I have is a two-form. And we can call this two-form the volume form. If you prefer, we could call it the curvature form. Or we could even call it,
volumes in, like if we do this in vacuum, you're saying volumes of Causal diamonds in de Sitter space are equal to areas of intersections of...
That's right.
Okay.
Yeah, that's right. That the volume of this region in de Sitter or in some other kinematic space, it doesn't have to be de Sitter, is computing exactly this quantity. And so it's telling me in this region of my tensor network, this is how many correlated lines I need to insert.
It's Lorentzian volume, is it? Lorentzian.
Pardon? That's right. It's a Lorentzian volume.
So is this one of those things that's obvious to derive if you think about embedding both the hyperbolic plane and de Sitter space into a higher dimensional
That's
space?
Right. So this is obvious.
This way?
That's true for the hyperbolic disk in de Sitter. I have no picture like that for general geometries. And so I don't know. Sometimes I think it's good to bring it up, but then I don't. I mean, it'd be nice if that was a general story. I'm not saying there's.
Think about it that way.
I'm not sure there's a general story like that. I can't tell you whether that's right or wrong, and so I've left it out. But if it's helpful, yes. I mean, that's sort of how you identify the right volume form, is that you want to choose the sort of unique form which is invariant under all the rotations in this higher dimensional space.
Just a clarification question. So these pictures are in kinematic space?
These pictures are in kinematic
space.
space.
ABC were regions in the original field theory, so they still
That's right.
remain regions?
So you can still, there's a one-to-one identification between the boundary of kinematic space and the boundary of real space. You can think these are just tiny intervals, and so they're really, you can identify some sort of the infinitesimal limit of some interval as a point in that space. But really sort of all of these lines are, carrying information about some very small interval. So for an arbitrary choice of entanglement entropies, we can use the corresponding volume form to add lines to our network, like this. And we can sort of guarantee that we can exactly reproduce all of the single interval entropies of your state. You might ask, have we now succeeded in reproducing the state with our tensor network? The answer really is a resounding no. So while we've fixed the isometries, what we haven't done is said anything about the role of disentanglers. And so, without the disentanglers, it's not at all like a geometric state. I have really long-range correlation, but that's correlation sort of between, UV degrees of freedom varies far apart. And what we really need is that the correlation at large scales is sort of, with these degrees of freedom, sort of commensurate with their separation. And so this is the role of disentanglers. What disentanglers are really doing is taking correlations created in the network and distributing sort of inside the light cone. I'm going to skip through this because I'm short on time. But if you're interested, I can tell you more. That there really is sort of there's other measures on your tensor network that measure the degree of mixing. And what's sort of beautiful about geometric states is that although I may have different geometric quantities that tell me about the correlations between the different disentanglers, in a geometric state, they all reduce to the same form. And so there's really only one piece of information. While for a general tensor network, I need lots of different data to specify what's happening. And so that's sort of a beautiful fact about states as geometric duals, that all of the information about the tensor network is encoded very simply by one geometry, and that's kinematic space. And you should think about this sort of as being like the beautiful fact about geometry, that all of the entanglement entropies for n intervals are given to you by the entanglement entropy of single intervals. And so it's the same sort of collapsing of information that happens in both. So I'd like to finish just with a 2-minute statement where I'd like to just sort of give one implication about this picture, which I think is very interesting. And that's about the Bianchi-Myers conjecture. So if you recall, one of our aims was to better understand what holographic entropy is counting. And the Bianchi-Myers conjecture suggested that we should assign some entanglement entropy A to the factorization of the Hilbert space corresponding to the degrees of freedom in some orange region and its complement. And so the entropy for this orange region is meant to be given by the length of its boundary. That's its entanglement entropy. And if I do something similar, I take some blue region, where here I've just sort of made some excursion into the interior. But this is meant to have a larger area, and so it's meant to have a larger entanglement entropy. So this is something I think that's very natural from the perturbative perspective, where we're meant to have some large contribution from the entanglement entropy between sort of degrees of freedom that live on either side of the surface. And if I make the area larger, the entanglement entropy should increase. That's sort of a natural perturbative intuition. You might ask, from the perspective of tensor networks, which are really some sort of non-perturbative tool for understanding quantum gravity, does this hold in the same way? The answer is really no. So the non-perturbative perspective given to us by MERA and kinematic space sees the counting very differently. So the spike makes our surface non-convex. And so the spike, we should think about some region of kinematic space like this, while the convex surface is some region of kinematic space like this. Actually, here, let me just draw on here. So if we remove this region, that's not working. Hold on. N. Here we go. So if we remove this region of the tensor network, then there's a state that lives on its boundary, whose entropy is given by the number of cuts along this edge. But what happens when I go to the non-convex surface? I do have a number of cuts along this edge, and so I can prepare a state for that convex surface. But these extra cuts on the non-convex region, which were the increase in the area, these don't correspond to any new states that I can specify. The state that filters to the UV is completely specified here. And so the only sort of contribution to specifying states on that additional cut really should be viewed as some constraint. So what I'd like to say is that only in special situations for convex regions should we associate an entropy to a region of space-time that's proportional to the area. And MERA and the more general kinematic space agree on some refined space-time entanglement proposal, and it really gives markedly different entropic interpretations to different regions of space-time. I should say that really this sort of suggests that the Hawking pair picture at high energies is really incompatible with this counting. This is something we might want to do around any surface, and this is saying that if we sort of did this all the way up to the Planck scale, that we would get the wrong answer for the entropy. And so this has to fail far below the Planck scale in some limit in which we would have expected it to. This is just some sort of non-convex region I chose in space-time.
Isn't the covariant entropy bound supposed to work even if the regions are non-convex or whatever?
I mean, if you're making a statement about perturbative quantum field theory on a curved background, this has nothing to say about that. This is really some statement about non-perturbative quantum gravity. And it's really a statement that disagrees with doing effective field theory, doing quantum field theory on some curved background.
Covariant entropy bound has a non-expansion condition that's a lot like this convex.
I'm already over my time. I know I've gone 5 minutes long, so I'm just going to stop here. But yeah, I'd just like to say that this is a very sort of interesting non-perturbative consequence of thinking sort of very, of thinking very seriously about tensor networks and their implications for geometry. So thank you.
Suppose your concavity was not a spike, but was just smoother. Are you saying it would be almost scalar
It'd be very
area, but not quite?
Yeah, that's right. It would be similar. I mean, part of it is that we need to. What we're allowed to do is now talk about what we mean by entropy. So we have these double counted regions. If we just took the single counted region, it would be close to the area. And your area would be differing by some measure of the cuts here. And how we want to interpret those as constraints is something that we could, I think there's still some room for us to decide. But what's certainly not true is that these extra cuts give no more freedom down here.
Maybe I should have understood this earlier, but the Sitter symmetry of kinematic space, where is that coming from? If I start with a hyperbolic disk.
The easiest way to see that is to think in the embedding space picture. So,
but is there an isometry that acts on it?
Pardon? Yeah, it's the same. There's the same isometry that is rotating the intervals. So.
But the Sitter has a different isometry group than the anti-Sitter, or do they have?
No,
it's the same.
It's the. Yeah, it's the same. It's just the isometries that you get from the embedding space. So if you think, well, the easiest way to think about it, if you want to talk about some geodesic in the hyperbolic disk, the way you do it is you take some plane through the origin that cuts it, and now look at the normal of that plane at the origin. This picks out a point on the de Sitter, the other hyperbolic slicing of that geometry.
But that's special then, again, to the dimensionality.
That's special, yeah. And so the question you might want to ask, what is the causal structure about in spaces without that symmetry? And I think I gave a good understanding of an intuitive way to think about that causal structure. And it's about whether or not intervals are contained in each other. And that's something that is sort of invariant under the various rotations one might do to a space with symmetries.
Sorry.
Have you thought about thermal states?
Yes, we have. We've thought about thermal states in several different ways. I think there's very interesting things one can say about thermal states.
So you got normally you think about it as a long flat region, right? And the tensor network, that is. Yeah, so
there is one tensor network that has arisen from this idea of tensor network renormalization, where I obtain the MERA-like tensor network from doing some coarse graining scheme on the Euclidean path integral. And this builds you a tensor network for the black hole. It's one that's not so useful, I would say. And I would say it's not so useful because what we really want to understand in the black hole is, say, regions near the horizon. And also say, and what I mean is that geodesics that probe near the horizon, and these are geodesics that wrap around the horizon. I'd also be interested, say, in geodesics that pass through the horizon. Now, all of that information, it seems to be encoded in just a row of tensors in the center of that network. And so what I really need is some scheme that takes that row of tensors, which builds the thermal entanglement, and I need to break it apart. What I need to do is some scheme, like my compression scheme, that gives geometric meaning to the different pieces of that center network. So we have some preliminary results that we're in the process of writing up right now that'll tell you one way that you could imagine breaking those apart. So this is actually very interesting, I would say, in particular, because one thing we need to supplement our picture of kinematic space is some entropic quantity that corresponds to something like long geodesics, to entwinement. I need sort of a general understanding of what entwinement is. And there are sort of definitions given in very particular cases, but they don't generalize. One thing I could do is if I was able to give you a tensor network for a black hole state, and it had these extra geometric regions to it, what I could then do is use that tensor network to sort of operationally define entwinement. I could actually look at one particular tensor is doing and see how changing that affects the state, and this would give us at least some intuition about what entwinement should mean. And so this is something we might be able to say something about in the near future.
All right. Well, thanks again.